Welcome back to another video about Baluns and common mode chokes, which is a continuation from the previous two videos. There's more to this topic than you might think, and I hope you'll stay with me. The previous video, number 81, showed that the heating effects of a balun were directly due to the common mode voltage across the balun. There is also an indirect heating from the wire due to the total current flowing in the balun, where some percentage of that heat increases the core temperature. This is nearly all from differential current, since the design of the balun is to reduce common mode current. I hope everyone realizes that the measured impedance of any real antenna is a function of the distance from the antenna to ground. The typical two-terminal measurement of antenna impedance does not show the effect of ground and predicts a common mode current always equal to zero, which would mean a balun would never be needed. We know that common mode current exists and is measurable, so a better model is needed to allow calculation of balun stresses and the necessary balun choking impedances. This better model may or may not change the results of impedance matching to the antenna. So let's get started. Shown here is a three-terminal network comprised of three individual impedances, R1, R2, and R3, which can be complex numbers in SimSmith, so hence their impedances, and they're shown in a Y configuration. We could have done this in a delta configuration also, but we have the two terminals, W1 and W2, which are the end of an open wire line that came down from your antenna. Ground is the invisible connection that the antenna has to ground. And we have a network analyzer here, or impedance analyzer, or whatever. And we have one side of it connected to a ground stake or some ground screen or whatever to measure, basically it's intended to be at this same impedance. This point to this point should be a low impedance. And we're going to make three measurements. Those three measurements are going to be ZA, ZB, and ZC. ZA is what's shown in the schematic right now. We'd measure it, sweep the frequency if you wish, save it to a file, make a new measurement. The new measurement would be that circuit. We swap W1 and W2 around, where W2 is connected to the hot side of the analyzer, and W1 and ground are connected together to the chassis of the analyzer. And then finally we make one more measurement, and that's Z sub C, where these two are connected together, W1 and W2, and you make that measurement relative to the invisible connection to ground that the antenna has. And we save those three impedances. Now I did that for an antenna I had in the backyard, and I did it just at one frequency, so these are not files. They would be a file if you did it for a wide range of frequencies, but they were just an individual impedance. And then with a whole bunch, let me go back to the original circuit here for a second. Then with a whole bunch of ugly algebra, we can convert those three impedances that we measured to the equivalent circuit values for R1, R2, and R3. And it's pretty ugly to do that, and that's why there's some temporary variables here. But I will make this file available. And here's a little calculator I found online. This calculator does a Z1, Z2, Z3 calculation, which is exactly what this circuit looks like. And if we were to take the calculation we have for, let's just say, Z sub A, then R1 here is the same as Z1, R2 and R3 are Z2 and Z3, and you see that the result that we get with this calculator is 95 minus J160, 95 minus J160. And if you swap these values around, you would get the other two values for R2 and R3 that I also calculated. So I did the math right, although I didn't get it right the first time or two, but nevertheless the math is right. I will make the file available to be downloaded, the circuit in SimSmith, and you can play with it to your heart's content. So what is the real differential impedance of this antenna? If we measure the impedance from W1 to W2 using this circuit as shown here, we get the value of 95 minus J160. However, if we measure it like this, we get 91.6 minus J172. So when you measured the impedance of your antenna, what did you do? Did you have your battery-powered small antenna impedance analyzer connected to your laptop which may not have had a connection to ground, may have had a higher impedance connection to ground. Was it your transmitter in your shack, which may have had a very good connection to ground, may not have had an impedance to ground? Either one. Either way, putting a common mode choke in here removes this connection to ground here as far as the antenna is concerned if the common mode impedance is high enough. So 91.6 minus J172 versus 95 minus J160. Is that enough to change your matching network? It certainly changes the values a little bit, whether or not it's big enough deal to worry about or not. This kind of a issue does explain some problems. It explains the comment that I've gotten from some people where they claim to be very, very good at making impedance measurements. They make an impedance measurement, and yet the values they get aren't quite right. And it didn't occur to me for a long time that they may be encountering some of these kinds of issues. But nevertheless, it's just something to keep in mind. This is going to be fairly difficult to explain, but this circuit does two things. The first thing it does is create a locus of points based on an SWR that I can then calculate for each one of these individual points the voltage and current that will be impressed on the balun in any way I wish, differentially or common mode, it doesn't matter. And I do that with this simple function right here. And I save the value in L dot ohms right here, just for grins. I don't need to save it there. I'm not using it there or anything else. And then I have a balun. And in this case, the balun uses this circuit we just had a minute ago. It uses a percentage of what this value is based on this balance control. And if you watch these two values right here, you'll see as I change the balance control, they always are the same sum, but the percentage of them on each side of the center point varies. And I have the center point grounded, which would be the worst case for no antenna has a 0 ohm common mode impedance, but we're going to use 0 ohms because it gives us the worst stress on the balun, and it's also the hardest for the balun to equalize the two currents to the load. And we're going to drive that with a 1500 watt generator with an X match. X match means there's a tuner here driving this circuit. This is a 1-to-1 balun in a circuit where the balun is on the antenna side of the tuner. We'll move it to the other side, the transmitter side of the tuner later, and we'll see if there's any difference. I'll also do a 4-to-1 balun in a few minutes, and we can see the differences between all the different between the two different balun types, and you can do any different type of balun you wish to do. I'm going pretty fast with this, and I've done some of these things in the past, but kind of just go with me here for the moment. If I need to do another video that explains any particular details more slowly and more clearly, just let me know and I'll try to do a video to do that. But right now what I have here, and let's go to the square chart for the moment. Let's go back to 1-to-1 SWR. For 1-to-1 SWR, I can look at the voltages coming into this circuit. A 1-to-1 SWR with a balance of 50% has 25 ohms here, 25 ohms here. And let's look at the voltage we see. W1 is a oscilloscope plot of 1500 watts, which is 273 something volts RMS. And this is the peak values of that voltage. This is what's impressed on the balun right here between W1 and ground, which is what W1 plots. And then W2 is the output here, and W3 is the other side. These two voltages, when added up, give me the same voltage I put into the balun. It's a 1-to-1 balun. It's of length 1/1,000,000th of a foot long, so it doesn't matter what impedance I use for the balun. It doesn't change anything because it's such a short it's just such a short length. And I can change the length of the balun, and the balun will act differently. But right now, let's go with the smallest length possible. It's an ideal balun. It's got 1,000,000 ohms of choking impedance. So I have 2 million ohms on each side of this balun. This is what I have. The balun stresses would be the voltage from here to here, or the voltage from here to here, or in the case where I have length of transmission line here, I just use the average of those two voltages. And I calculate that with this function right here. This is done in RMS because we usually size cores based on an RMS voltage. So this RMS voltage represents this RMS voltage is half of what comes into the balun. So if this is V coming in, think of it this way. This is V coming in. This is plus V over 2 minus V over 2. When this is minus V coming in, this is minus V over 2 and plus V over 2 down here. With this being, there's always V across here if there's V across here, and it's just level shifted. And that gives us the nice balance that we see. And if we look at the current that flows here, we'll see the two currents being equal and out of phase. And they are, very nicely. So what happens, and we can turn off the actual waveforms right now. Let's just look at this plot. What happens, well, let's move it down to 0. What happens is I increase the SWR effectively that my load presents to my balun. Every time I double the SWR, the voltage rises by the square root of 2. So let's go back here to 1-to-1 SWR. And we see that this is 137 volts. Go to 4-to-1, it's 273 volts, etc., etc. And if we go, let's go to 10-to-1 for a minute. At 10-to-1 SWR, we see a maximum voltage at 432 volts, a minimum voltage here at about 43 volts, 432 volts, 10-to-1 SWR. Things just, things work the way they're supposed to work. Now, is a 10-to-1 SWR a good range of impedances to match to, or do I need to go higher than that? Well, you actually need to go probably up to maybe 50 or 60-to-1 SWR, and I'll show you why in a minute. But at a 50-to-1 SWR, what the balun sees, and it sees the most voltage at the zero degree phase point. The 0 degree phase point is that point right there, high impedance, high voltage. Over here, low impedance, high current. So for right now, let's go back to this. We see this being 967 volts RMS at 1500 watts. If we were to provide a load that had this impedance, a 50-to-1 SWR again down here, it's right there it is. Now let's go over here, and what we see, we're over here now. Well, it's hard to see, but you can see the dot moving down there. The dot's right here. In this case, we have high current. The current at this point is huge. It's 50 some amps peak, which is a huge current, and we clearly are going to have a hard time feeding any antenna through any normal feed line. So for the moment, what I've shown is we have high voltage across the balun here. The voltage we have across the balun is half of what the differential voltage is. And the differential voltage determines insulation requirements and stuff in the wire, but it doesn't put any stress on the balun. The common mode voltage here puts stress on the balun and causes heating. So why might we possibly need to accommodate impedances that are this crazy? In this circuit, we have a file that we're loading in as an impedance file for the antenna. We're going to assume the antenna is just a 2-terminal device here. It's a 136-foot piece of wire, 12-gauge copper wire, 40 feet high, and it's flat. It's a flat dipole, and it feeds open wire line, which is 350 ohms. Let's make it 500 ohms. 93% velocity factor is reasonable. 0.05 dB per 100 feet. Loss, I don't know if that's reasonable or not, but it's not bad. And we're going to drive it with 1500 watts. So that's, first of all, what we're plotting on the pink curve here is the impedances we see starting down here at 1.8 megahertz, which is incredibly bad impedance to try to match to. It's 22 minus J 1040. I have a line here shown on the Smith chart, which is a 50-to-1 SWR. We have a lot of points here in this graph that are outside the 50-to-1 SWR. If we wanted to use this antenna as a multiband antenna, and we had 50 feet of transmission line, and we varied our frequency here we would see that any frequency, let's go back and start at the beginning. At 3.5 megahertz, we'd have a nice impedance to match to. 4 is okay. Let's go to 7 megahertz. By the time we get to 7, we got a very high impedance here, and it's going to be somewhere in that range, 94 to 1 SWR. These impedances are impedances you would see on open wire line if you had an antenna that was this size. And you say, of course, it's stupid to have an antenna that's 136 feet long. It's exactly, a full wavelength on 40 meters, and et cetera, et cetera. So let's just keep in mind all this graph. Now, these impedances are the impedance at the antenna. If I look at the impedances here at the generator, we can do that too. We'll take away these impedances. We still see the same range of impedances. There's rotation involved due to this transmission line, and the rotation occurs about the center point. That's 500 ohms. It doesn't do a center. The rotation isn't exactly about the center point as you might think. And I did a video on that earlier, but it rotates around this 500 ohm point. And we still see impedances that are outside this we're darn near 100 to 1 SWR down here for some frequencies. So what can we do about this? And the answer is, based on the kind of tuner you have, you may not care. But we have high voltages here and very low currents. And that was always the claim to fame when people used to use like a Johnson matchbox, and they'd say, throw up a 135-foot dipole and feed it with open wire line. If we change the impedance of the open wire line, what happens? Well, if we drop that impedance down, we've moved all these lines a little bit inward. That has helped us. It causes this transmission line to be a little bit more lossy, probably, because the currents on it will be higher. You're definitely going in the right direction by making that a lower impedance. Another thing you can do is you can try to change the length. So I modeled a bunch of other lengths. Let's go to 130 feet and see. Well, before we go there, I've got the line set right about at the asymptote here of the maximum. Let's see. Let's go to a 100 to 1 SWR. Look at that. We're just about at the 100 to 1 SWR line there. So what happens if I put a different length dipole? I cut 6 feet off the dipole. What do I get? It moved in a little bit, but not much. Let's go to 120 feet. Maybe a little bit more improvement. We're hurting the low frequencies, but we're not going to use this on 160 meters ever. We're just going to use it on 80 meters at the low frequency. What would happen if I would go to, people say 105 feet. That's a special number you see sometimes. Well, that's helped a little bit, so that might be a good idea. I mean, the pattern changes, etc., but we're looking at impedance only. What about 88 feet? 88 feet's gotten worse. And of course, if we go to 66 feet here, it's going to get worse again. But it gets worse at a frequency of about, it's hard to say what's coming in here, at about 6 megahertz. So it'll be worse on 80 meters, which would be, 80 meters would be up here somewhere, 3.5. So somewhere out here, at the high end of 80 meters, we're over the 100 to 1 SWR again. So it's very high voltages. This is the reason why some people say use a 4 to 1 Balun. And we'll look at 4 to 1 Balun in just a minute too. One thing I can do that's appealing is you can try to do something like, here's a 120-foot dipole that's 4 inches in diameter. Now you can't get 4-inch diameter copper wire, but what you can do is put a couple wires up there, and it'll achieve a diameter that's larger than a single wire. So a couple wires in a cage will be better, and that helped a lot. So now my lowest frequency down here is below the 80 meter band, and by the time I get to 80 meters, 80 meter band is pretty close to being right on the edge. Maybe I'd make this a little bit longer, but all the other frequencies are much easier to match and lower Balun stresses. So this might be a good plan. You can also try a multiple wire dipole. You can try other things. Lots of choices of things to do. This is kind of a very interesting example to mess with, and people have done this for years. They've come up with a certain length of transmission line that's, quote, their favorite. And there's certain ones that have certain characteristics and certain impedances. You can notice if I drop my impedance to 350 ohms here with this effective 4-inch diameter wire, now I'm quite a bit below. I'm down in the 47 to 1 SWR range. 50 to 1 to 100 to 1 SWR is a 1.4 difference in voltage. So that makes my Balun requirements much, much easier than before. So that's, it's another thing to do, but you really can have a lot of fun with SimSmith doing this kind of stuff. Is 56 feet a magic length? I don't think so. I mean, we can just see. Now I could put dots on here for all the different frequencies I wanted to and look at wherever I was up here at the highest impedance point, which would be the most stress. But no, without doing that, you can see that there's a lot of things you can do. But nevertheless, let's just go right now and look at a 4 to 1 Balun and see if a 4 to 1 Balun really helps us at all. This circuit shows a 4 to 1 Balun, which is built from 2 single 1 to 1 Baluns wired in a way that the transmitter sides are in parallel and the secondary are in series. And that doubles the voltage, which quadruples the impedance. Hence a 1 to 4 or 4 from the load side to 1 at the generator side impedance. And if we look at what's going on here, similarly to how we did it before, I have the same control circuitry I had before where I could generate various data points and I could use that to calculate the voltage and currents across the any part of the circuit I wish to. Let's look at that. So the first thing I'm going to do is look at the voltage on the input side, and we'll look at the W. This is kind of hard to see. W1 represents W1 to ground, which is plotted as W1, is now a little less than 200 volts peak. It was higher than that before, but we'd expect that. For the same impedance, which is a 50 ohm output impedance, we see 12.5 ohms here, so we need lower voltage than we needed before. It'll be higher current, of course. And the output of the Balun should be exactly the same as it was before. And that's the same 190 volts peak, and an opposite value. Now let's try to, let me see if I can, that goes, there's half. And here's the 1 to 1 Balun back again. See if I can get both these on at the same time. That's close. Make this a little smaller so that the square chart gets a little bit bigger. Not quite the same, but it's close. So on the 1 to 1 Balun, which is on the right side, we see a 380 volt peak signal, which is twice the peak signal we see driving the 4 to 1 Balun, and we see the output voltages being the same. Now let's look at the stress on the two individual Baluns in this 4 to 1 circuit. On the first one has no voltage across it. Very interesting. So we go back here, and let me bring the circuit back up. We're looking at, if this voltage is half what it used to be, and this voltage is the same as it was in the 1 to 1 case, then there'll be no voltage across here. So that's very interesting. So there's no stress on the Balun that's on the top side of the circuit. The Balun on the bottom side of the circuit sees the red trace, which is about a little less than 200 volts peak. And in this one over here, the 1 to 1, the Balun sees a little less than 200 volts peak. So the bottom Balun in the 4 to 1 Balun, the bottom choke in the 4 to 1 Balun, sees the same stress as the 1 to 1 Balun. This needs to be wound with perhaps slightly larger wire if the impedances are lower, maybe not, depends on where you are on the Smith chart. And the input signal voltage is half as much. That means it may be easier to match, in the case we just showed where all the impedances were over on the right-hand side, it may be easier to match this circuit than it would be this circuit. But from a Balun point of view in terms of stresses, there's no advantage to going to a 4 to 1 Balun. If we look at this a little bit different, let's change this circuit to be like a 3 to 1. We can see the impedance at the load side here is this typical circuit we'd see for 3 to 1. And then at the generator, we see the impedance is mapped over to this range. Whereas in the 1-to-1 Balun case, the load impedances are right there, and the generator impedances are right there also. So it's, there's not a lot of compelling reason to go to a 4-to-1 Balun, in my opinion. You may have particular cases where you can't match with your matching network, in which case the 4-to-1 Balun makes a lot of sense. But let's look at some extreme cases here. So let's go to a 50-to-1 SWR on both of them. And let's look at the maximum voltages across the Baluns. So remember, let's just look at just the stress on the Balun and just the stress on the Balun. We see the same amplitude signals. Both of these have about a 1368 volt, which is the same as 968 volts RMS across the Balun. The upper one, in this case, could be wound on a very small core, or no core, actually. It wouldn't need to be. And let's look at what happens in terms of stresses as we change the imbalance in the load. If we drop this to a 0.4%, or excuse me, 0.4 balance versus 0.5, again, the worst case choke here sees the same stresses. We go to 0.6. It sees more than it did at 0.5. If you had a circuit that you knew your antenna was imbalanced in a certain direction, you could swap the two leads to the Balun and turn that into that, if you wish to. Let's look at, with a 50% balance point, let's look at what happens as we start to drop the impedance. Let's drop the choke impedance on the Balun to, say, 5 kiloohms in both cases. And now let's look at the current. Ultimately, the current is ultimately what we really care about. If the currents are equal, then the Balun has done its job. Okay, we see with the same choking impedance on each of the chokes, the same imbalance occurs. And a 5K choke is not a terribly good current equalizer. And that's part of the problem with the impedance being so high. If the antenna itself had some impedance, say 1 kiloohm, we'll see that this gets just a little bit better, but not appreciably. And 1 kiloohm is quite a bit of common mode impedance on the antenna. So we don't gain a lot there. Where we gain a lot in having common mode impedance in the antenna is if the choke is going to have a very low impedance. But 5 kiloohms is getting to be a lot of choking impedance, and we still see an imbalance. And people don't mention that very often, and that's exactly what happens. And making that higher than 5 kiloohms is extremely difficult. The imbalances are just incredibly hard to control. If you think about what 1 picofarad is at 30 megahertz, it's about 5 kiloohms. An imbalance of 1 picofarad somewhere in your circuit undoes that. In this case, the choke it's just the choking impedance. But if we were to build a circuit that we tried to make balanced on its own merit, the Johnson matchbox was never a very good balance. I measured the output currents on the Johnson matchbox, and they're not matched this well at all. But for most cases, that doesn't matter. It's picked like, say, 1 kiloohm. At 1 kiloohm, we see it's not terribly balanced, but it's not that much worse than 5 kiloohms. So that's something to be concerned about for the very, very high resistances. Now, if we were dealing with some other SWR, lower SWR, and remember, I've got the phase set to be the worst case. Let's set this phase to be something different. Let's set them both to be, say, 25 degrees. Got to get focus over here again. Now we see they're very well balanced. So it's really tough to build a balun that does its job when the impedance is extremely high. It's also extremely hard on the balun. And that's the only point I wanted to make. Now, people might say, well, of course this is going to be hard. That's why we put the balun on the transmitter side of the matching network. And let's go look and see what that does. Now, in this circuit, we have two specific circuits we're going to compare each other to. One has got the balun on the transmitter side of the matching network, and one has it on the antenna side of the matching network. And in the old days, the balun was always put on the antenna side of the matching network. And sometime in the 90s, people came to the conclusion that moving it over to their side was better. And then people debunked that idea, and some people stayed with it. And let's look and see what's really true. And there have been plenty of people who have big names who have advertised one way or the other, and there's really only one truth. And we can look at it, we can analyze it, you can make your own decisions. I'm going to do two cases, one with a low impedance, fairly low impedance, 25 plus J40, and then I'll do another one with an impedance much further over on the right-hand side of the Smith chart. The 25 plus J40 is up here in the center quadrant where the blue dot is shown on the picture there on the Smith chart. And what I want to do here is I calculate the voltage like I calculated it before. And at 1500 watts, this voltage right here, based on, show the circuit, a unbalanced L network. This inductor is just hanging out here in the air for a moment. And let's look at the SWR. SWR is 1 to 1. And the balun is here, so it's on the antenna side. Matching network here. The way we calculated the stresses before, which was the voltage at the balun, on the differential voltage across the balun divided by 2, gives us this value. Now in this circuit right here, let's just do it for real. What we're going to do is we're going to look at the voltage across the balun, R2 and R5, and we can see that plotted here where it says the voltage across R4. It's also equal to the voltage across R5. We can look at that several different ways. They will all give us the same value. There's the value. We see that they match at a 0.5 balance point. If I change the balance point, the original way I was doing it predicted the same stresses on the balun, but in fact the stresses change. And this is with an unbalanced tuner. What if I balance the tuner? I balance the tuner by basically doing this, putting the wire down here, and then I would change this value here to be half the value it was before. And what we see, let's see, make sure we're matched again. We're matched again. What we have is a considerable improvement in balun stress. We have lower voltage. So before we had, at this impedance level, which is 25 plus J40, before we had 182 volts across the balun, and that's at 1500 watts. And now we have down here 136. Much easier. This is a much lower voltage, less stress on the balun. Now, let's look at the second circuit. In the second circuit, it should look very much like the first one, except that the tuner is on this side. In this case, I had to change the topology of the tuner because it's where it sits in terms of things. But we can see that it's an unbalanced L network. And in this case, we look at the voltage across the choke here, and we see it's the same as predicted before, which was the input voltage divided by 2. And of course, as we change the balance point, it moves. Let's make this balanced. If we make this a balanced, that's very interesting. The same stress, if they're both balanced, or if they're both unbalanced, the matching networks, we end up with the same values, independent of whether the choke is before or after the matching network. And people such as Roy Llewellyn and Kevin Schmidt have published papers on this topic proving this. But the whole story, this isn't quite the whole story. And let me close these windows both off for a minute. If we change the length of the transmission line, and let's watch watch what happens here. As we change the length of the transmission line, all of a sudden, we see changes. The blue line, remember, was an estimate that we used when we first started, so the blue line really doesn't count anymore. These are real values that are calculated for the actual circuit. This is pretty interesting. As we add length of now you're never going to have 20 feet of transmission line in your Balun, but if we go to lower values, we see that there is differences. When the length is virtually zero, which is what they did in their analysis, it made no difference. If I'm going to put 4 feet in a Balun of wire, it's a little bit better for it to be this case. And this case was A, and A is the case where the Balun is on the output. You can have it where it's better on the input too at various times, but the point is it really makes no fundamental difference where the Balun is put. And just to continue on with that, let's do one more example. Now we have a circuit which has an impedance of 200 minus J800. A pretty high impedance, and it's way over here on the very right side of the Smith chart. And it occurs at an SWR that's 68 to 1. So it's a very high SWR. Let's see if it makes a difference there. What we're going to do, same as before, we predicted a value based on half the differential voltage on the Balun, and then we did a calculation. Here our calculation for the first circuit, which has the Balun on the antenna side of the matching network. And again, it's an unbalanced matching network in this case. And we see that the values match. So let's get rid of this one because that one's just an estimate. And we have to, I didn't finish this circuit up, so let's finish this circuit up here. I'll delete that line. I'll take this and copy it. Now, the inductance value is two times as large as it should be, so I'll divide both of these by 2. Got to divide it by 2. And we see the value is that. And that's considerably lower than what we predicted before and what the original value was. As a matter of fact, it's massively lower, which is incredibly good because this is the case where the stresses are much, much higher. So here's a case where we had originally 1,129 volts across the Balun, and when we went to a balanced tuner, a balanced network for a tuner, we dropped that to 136 volts, which is incredible. Let's look at the second circuit. The second circuit now has the tuner on the antenna side and the Balun is on the transmitter side. Again, we can do the same thing we did before. We get rid of this component. We'll copy the capacitor to make it symmetrical. Now, since these capacitors are in series, they really need to have twice the value they had before. Can check and make sure that it's still matched. Let's see what we'd have. It'd be SWR B now. It's 1 to 1. And let's look at the voltage on the circuit B. And it's exactly the same as the A circuit. Very interesting. Both of these had a huge improvement. So we don't need to have nearly as big of a Balun requirement if we're willing to use a symmetrical matching network. Rich Measures, who passed away last year, suggested this in several pieces of literature over time. It never really got a lot of traction. Some people built circuits that way. The problem with this, and I'll show you this in just a second here, is very simple, and that is can I build this network on the far side of the balun accurately enough to not have a problem? And what I mean by that is, what if I build this network and I have this accidental, say, 10 picofarad capacitor that's different. Let me make this circuit a little bit bigger. Just an extra 10 picofarads on one side of the circuit to the other. And the whole reason for having this is just the fact that you can't make it perfect. I mean, 10 picofarads is not much when you have these large components in a tuner. We can see that it affected the voltage a little bit, and it affected the SWR, and I'd have to retune this SWR to get it back down again. It's only 1.4 to 1. Let's see if I can retune it. Now it's down to 1.1, and that's probably close enough. But what I'd like to show here is the difference in balance. And what's happened here is, let's look at R1 and R2 for circuit 1, and R1 and R2 for the second circuit. So R1 and R2 for circuit 1 are balanced quite well. Again, because this is a huge choking impedance. But for circuit 2, we see that they're imbalanced due to this 10 picofarads. This 10 picofarads is getting in the way of the work that the choke is capable of doing. And that's always the problem with putting the balun on the transmitter side. You have to be incredibly meticulous in your design here if you wish to achieve the full value that the balun can give you. Now, this is with baluns that have a 1 megohm choking impedance. What if we take the, and this is just a resistive choking impedance. I could make it reactive. It wouldn't matter. Let's drop this down to, say, 5 kiloohms and see what happens. It didn't really change this too much. That's nice. And these two are still better matched. But the 10 picofarads is probably a pretty reasonable number for a low-end unbalance with circuit like this. Also, if you want a low-pass topology here, you're going to be stuck with 2 roller inductors, perhaps, or a more complicated. It's a more complicated circuit. In my opinion, it's really not worth trying to put the balun on the transmitter side generally, but balancing the circuit before, so going to this circuit where with a balanced network and a much smaller common mode choke here for a balun is very appealing. Our transmitters today really do not require us to have a low-pass network here for harmonic reasons, and which is why the high-pass T-tuner has become so popular. Putting a symmetrical matching network here and a much smaller balun is one way to go. The other way is brute force, an unbalanced tuner, and just make this matching network extremely make this balun much larger than it would otherwise be needed to be. But then you can handle the incredibly high impedances that you will get potentially with a loop or a dipole and open wire feed line at certain frequencies. This video has been pretty hard to make. I struggled with how to present this information. The files will be available in a link. There'll be a zip file that will have all the files in it. You can play with them, and if you have, obviously there's going to be questions. If you'd like me to address a different piece of this more slowly and in higher resolution, perhaps, let me know. Otherwise, feel free to play with this and see what you can figure out for yourself. Thank you very much. If you've made it to the video for this long, it's getting to be a pretty long video, and it's pretty complicated stuff. And I question whether or not I really am doing a service to anybody by making it this complicated. but unfortunately this is part of the reason why the topic is not very well understood. Thank you again. If you like the video, please give me a thumbs up, and please comment if you, the direction I take the channel is somewhat a function of what the comments I get are. Thank you again.